to my talk. So, who knows the joke about the nun and the elephant and the German in leather pants? So I can't tell you this joke right here, but check out the Datameer booth. Maybe I'll tell you there. Yeah, my name is Henning. I'm working at Datameer as a data scientist. And this talk is about histograms. And actually, when my coworker entered my office and said, hey, Henning, why don't you talk at Hadoop Summit about your histogram stuff? I was like, really? Histograms? That's boring. There will be zero audience. So, well, this is different from zero, right? Yeah, welcome. This is about how to create histograms from a data stream by MapReduce. So let's begin, very basic. What is actually a histogram? I guess most of you know this. It's just a visualization of your distribution of the random variable from some data. And one important thing here is that the area of the bars, of the bins in this histogram are actually proportional to the frequency count in this bin. And in order to create a histogram, it's a pretty straightforward and pretty simple procedure. What you do is you actually get your data, and first of all, you pass all the data in order to determine the minimum and the maximum value to be able to actually determine where the bins are, to set up an equal width bins in your histogram, and then you pass all the data again and throw them into the bins and count the frequencies in the bins. So this is a pretty straightforward approach in order to create a histogram. Now, what can a histogram be used for? Well, there are many use cases. Here are just some examples. For example, you can use it to optimize your data processing for example, in a distributed environment like Hadoop. For example, you can use it to optimize your joins. When you know the distribution of your data, you could try to optimize your join strategy, or you could use it for probability density estimation. Basically, what you do there is you take your value and estimate the probability based on the frequency count in the corresponding bin in the histogram. Or you can use it for machine learning algorithms. For example, when you train a decision tree, you have numerical values. You want to determine the split point for the node in the tree. Or you can use it for naive Bayes if you have continuous valued attributes. Maybe you want to discretize them. These are all use cases, but probably most important for the user of a software like Datameer, for example, is you want to get a visual impression of your data just with a quick view to the histograms. So, and this is where histograms help a lot. So this is just an example of some Twitter data. So what you can see here, for example, is just, well, this is not very surprising. There are many users that have just a few followers and only a few users that have many followers. But what might be a little bit more interesting in this example is, okay, the user ID in this Twitter data set, what I have here, is obviously not equally distributed. And that might be interesting for me for some reason. And I just can see this in a second by watching the histogram. And I cannot see it by just looking at the column of thousands of numerical values, right? So this is what histograms are and how you can compute them and what they can be used for. Now, why do I give this talk? Because, I mean, this is pretty simple, right? These are all solved problems. So in our environment, the conditions are different. In our environment, data arrives as a stream. We want to create histograms during an import job where we see every single record once anyway, but only once, not twice. So this is a little problem because in order to create a histogram the usual way, you need the minimum and the maximum. You need to pass your data once to determine this, and then again to determine the frequencies. But here we see the data only once. So this is a data stream problem. Then another problem is the data is distributed on your Hadoop cluster potentially. So you need to find a strategy to actually combine the histograms when they are partly distributed, partly computed, distributed, and then combine them to the final histogram. And also, since these algorithms probably need some parameters, but we do not want to have any user interactions, we need to figure a way to either set the parameters to a constant or drop them, throw them away that we do not need them. So these are conditions under where we want to compute some histograms. Now, this is how I'm going to explain to you how we actually do it. The streaming solution, computing a histogram from a data stream but not in a distributed environment, this is actually solved by Carlos Pinto and João Gama. They developed the partition incremental discretization algorithm. We adopt this algorithm, but this algorithm requires some parameters. Since we do not want to have any user interaction, we also drop these parameters. I explain how we do this. Then, of course, we need to distribute computations. I will show how we combine histograms when they are computed on different nodes on a Hadoop cluster, for example. And since this approach is approximative, there is an error in the estimation of the histogram. So the result is actually an estimate. It's not the real true histogram. And we did some experiments for evaluation to show that the estimate is actually a good estimate. There's only a small error. Okay, so this is the partition incremental discretization algorithm. I will briefly explain it. It's pretty straightforward. What you basically do here is you maintain two lists of values, the bin breaks and the counts in the bins. And what happens when from your data stream a new value arrives, then the counts in the corresponding bin gets increased by 1. Now, there's a threshold where when the threshold in this bin gets exceeded, then there's a splitting condition when, for example, let's say the threshold is 10, then this bin needs to be split up. Now, two things can happen. Either this bin is a border bin, like in this example, then the bin breaks get extended at the border. Just another bin break is added with a certain step. So here in this example, the step is equal to 1. And the count values are divided into halves, and then the count is updated this way. So what also can happen is that the frequency value in one bin in the middle somewhere exceeds the threshold. So in that case, we have a split in the middle, and here we just do kind of the same thing. We split the bin in half and also divide the count in half. So this is the first layer in this approach. We have an intermediate histogram here, and now when we have our data stream, and at some point during this data stream, we want to compute the final histogram from this, we just aggregate this unequal bin width histogram to an equal bin width histogram, which is straightforward, and then we have the final result. So this is an approach from Gama and Pinto, computing a histogram from a data stream. And as you can see here, two parameters are required, alpha and step. And since we want to get rid of these parameters, since we do not want to have any user interaction, we need to adjust this approach a little bit. So let's have a closer look to the splitting condition, to the threshold. What you can see here is a bin is split when the count in this bin compared to the total number of values observed until this point exceeds a threshold. So this means actually that the smaller this threshold, the more often a bin gets split, which in turn means that we have many more bins, and the estimate of the histograms gets more accurate, so the error gets smaller. So this basically means set the bin as small as reasonable and as possible, and the error will be small. So we just say, okay, let's set it to a small constant, like, for example, 0.01. And the parameter step, we can get rid of this parameter by just maintaining the minimum and the maximum values from the data stream. And whenever a bin at the border exceeds the threshold, then we do not extend the bin by a fixed step size, but we just extend it to the new minimum or maximum value and split and split it also. Now, what we find interesting, well, first of all, a colleague just told me, don't go through these formulas, I will fall asleep immediately. So let's get rid of them. But still, I want to give you the basic idea of this. So we also investigated how many bins actually there will be. So what you can see here and what is also intuitive, of course, for the first n values in your data stream, of course, the bins will always split because there have not been yet enough values so that the total count is actually large enough that the threshold does not hold anymore. So for the first n bins, it will always split, but at some point, the first bins will not split anymore. You can see this in the corner over there for alpha equal to 0.01. And then the number of bins increases very slow, right? So this is actually computed for an example of a uniform distribution, but this holds also for other distributions of your data. Now, this is how you update the layer 1, your intermediate histogram. Now, what we want to know is, let's assume these are two different layer 1 histograms with different bin width and frequencies. And we want to combine them to actually get our final histogram, right? Because we're in a distributed environment. So what we simply do here is we align these two bin breaks. And since we want to keep the property of a histogram that the actual area of the bins is proportional to the frequency count of the histogram, we simply break all these bins up wherever a bin break occurs, either in the one or in the other histogram, and have all these tiny areas, and then we just sum them up to get the final combined histogram. So here's an example how this looks like in real data with a normal distributed column of values. So of course, and this is also intuitive, when there are more values, more splits happen. That's why in the middle of this histogram, this intermediate histogram, there are more splits, and to the border there are less splits. So the bins are wider. All right. So again, let's get rid of the formulas. So for evaluation, to actually investigate how accurate our histograms are, we did two evaluation measures. Affinity coefficient, it's the same as Gamma and Pinto used in their paper. It's based on you take one bin of your histogram and compare it to all the other bins, how much mass this bin has compared to all the other bins in your histogram. And you do the same with the original histogram, so you always compare your estimate and the original histogram as it would have been if you compute it exactly. And then you compare them with the affinity coefficient. Basically, this coefficient is equal to 1 if the two histograms are completely equal, or it is more close to 0 if there's a bigger difference between these histograms. And similar, the percentage error, but just the other way around. This error is, of course, better the better, the smaller it is. With the percentage error, we simply compute the fraction for each bin, how large it deviates from the original histogram. So we take our estimated histogram, look at every bin, and compute the deviation of this bin from the original histogram, the exact histogram, and just compute the percentage error this bin deviates over all the bins. So here are some experiments for different distributions. And what you can see here, maybe it's a bit small, but every bin here has been computed for the original histogram, for the exact histogram, then for the partition incremental discretization version from Gamma and Pinto, and then for our adjusted version in a distributed environment. And as you can see, there's always a small error for each bin, but it's always small. It's a bit larger for the border of the histogram in the normal distribution case. It's almost 0 in the uniform distribution case, and here for the log normal distribution, it's also not very significant. So also, we compared our algorithm, our adjusted algorithm, to the streaming version that is not distributed for different values of alpha. And here for each box plot, you can see, so each box plot corresponds to 100 runs of the algorithm. This is actually for the uniform distributed case. You can see that for a small alpha, like 0.01 or 0.02, the error is always less than 2%. But of course, when you have a larger alpha, so that splits occur less often, then the error increases. So we did this not just for the uniform distribution, but also for normal and log normal distributions and more distributions. This is just an example of the experiments we did. And what you can see here, of course, also the error depends on the distribution of your data. So what you can see here is, of course, for the normal distribution, the error grows faster with increasing alpha. But again, since we just use a small value of alpha, like 0.01 or 0.02, no matter what the distribution is, the error is always small. But if we would use a larger alpha, then, of course, the error would increase much faster. So just a quick summary, what I told you. We brought together the PID algorithm, which is a streaming version of computing histograms, with MapReduce in a distributed environment. We dropped all parameters. This is an approximative method, but we could show that the way we set the parameters to constant values, the error is small. Yeah, thank you for your attention. Now it's time for question and answers.
I guess one question is, I'm just trying to understand, like, if you are computing histogram by even in the streaming fashion, if you are on the map side, if you are generating the counters for each of your key, and on the reducer side, you are basically generating equisize histogram, what's the inefficiency you are seeing in that kind of approach versus, and what's the motivation in that case?
Yeah. So you mean in terms of performance, or?
Yeah, in terms of.
Yeah. So of course, since yeah, we would like to take advantage of the fact that we pass all the data anyway during import, right? But still, of course, when you do some additional computations on each record, there's an overhead. And in our case, we could observe that the overhead is about something between 10 and 20%. So you slow down your import a little bit, but still this is much less as compared to if you compute your histogram afterwards, where you need at least 2 passes over the data. So basically the answer is the slowdown is about 10 and 20% per histogram, per numerical column.
So are you generating multiple such histograms from the same data set, or?
Yeah, so if the data set contains multiple numerical columns, let's say 5, okay, then 5 histograms are computed.
Nice. Thank you.
Hi. So do you have any ideas on how to implement in a similar fashion, the CDF estimation instead of PDF?
You mean probability density estimation?
If you are interested in the cumulative probability, so if you want the percentiles or the median,
yeah, yeah,
and you not necessarily want the probability density function.
Yeah. I haven't yet thought about this. Maybe this is one of our next projects. Actually, I would like to talk to you and get your ideas about this afterwards.
Thanks.
Hi. Do you know if there's a sampling-based extension for the same method, where you're not reading all the data, but you're only sampling part of it?
No, we always read all the data.
Okay. All right. Thanks.
Can you explain again how is it that you get the breaks to align from the different map jobs?
Yeah. So basically, for each intermediate histogram, you have the minimum and the maximum break, and you just align them in a way that if you extend the breaks from each histogram, that they are just aligned to each other. So let's say there's a break with a value 10 in one histogram, and it's in another histogram. We just align them so that we actually can combine them based on the areas. Okay. All right, then. Thank you very much.